In the profound silence of the night, as stars quietly hold their vigil and the earth drifts into deep slumber, our minds often wander to the infinite questions that compel us to ponder the vastness of this universe. Among these grand inquiries, one concept stands out for its elusive nature and profound impact on our existence: time. What is time, really? Is it a fundamental force, a dimension we traverse, or merely a construct of our perception? Today, we will delve into the depths of this calm cosmos and attempt to understand the true essence of time. A journey where science and philosophy converge, bringing us closer to the heart of this eternal mystery. Our everyday experience of time is linear and unidirectional. We perceive it as a constant flow, moving from the past through the present and into the future. This intuitive understanding is deeply ingrained in our language and our consciousness. We mark its passage with clocks, calendars, and the rhythm of day and night. Yet, beneath this seemingly simple surface lies a complexity that has puzzled philosophers and scientists for millennia. From a classical physics perspective, time was often viewed as an absolute and universal constant, flowing uniformly for everyone, everywhere. Isaac Newton, for instance, conceived of absolute time as an independent entity, existing without relation to anything external. This view provided a robust framework for describing the mechanics of the universe, allowing us to predict the motion of planets and the trajectory of projectiles with remarkable accuracy. However, the early 20th century brought a revolutionary shift in our understanding with Albert Einstein's theories of relativity. Einstein shattered the notion of absolute time, revealing that time is not a separate entity, but is interwoven with space, forming a four-dimensional fabric called spacetime. This fabric is not rigid but can be warped and curved by mass and energy, leading to phenomena like gravity. One of the most astonishing implications of relativity is time dilation. This means that time can pass differently for different observers, depending on their relative motion or their proximity to a massive object. For an observer moving at a very high speed relative to another, time will appear to slow down for the moving observer. Similarly, time passes more slowly in stronger gravitational fields. This is not just a theoretical curiosity. It has been experimentally verified and is crucial for the accurate functioning of GPS satellites, which must account for these relativistic effects. This discovery fundamentally changed our perception of time. It is no longer a universal clock ticking away uniformly for everyone. Instead, it is a flexible, relative dimension, intimately connected to the observer and the gravitational environment. This raises profound questions. If time is relative, does it truly exist independently of our observations? Or is it a manifestation of the interactions within spacetime? The concept of spacetime also challenges our intuitive understanding of past, present, and future. In a four-dimensional spacetime, all events, past, present, and future, can be seen as existing simultaneously, like points on a map. Our perception of time's flow might simply be our consciousness moving along a particular path through this fixed landscape of spacetime. This view, often referred to as block universe theory, suggests that the future is not something that is yet to be created, but something that already exists just as the past does. This perspective can be both liberating and unsettling. If the future already exists, does that negate free will? Or is our journey through space-time, our experience of choice, an integral part of the universe's predetermined unfolding? These are questions that bridge the gap between physics and philosophy, inviting us to contemplate the very nature of causality and destiny. The calm cosmos, in its silent grandeur, allows us to ponder these intricate connections between space and time. It reminds us that our understanding of reality is constantly evolving, and that the boundaries of knowledge are always being pushed further. The journey to understand time is in many ways a journey to understand the fundamental structure of the universe and our place within it. Beyond the macroscopic world described by relativity, the quantum realm offers an even more perplexing view of time. In quantum mechanics, the concept of time becomes incredibly subtle and, in some interpretations, almost disappears. At the most fundamental level, the equations of quantum mechanics do not seem to have a preferred direction for time, and some theories even suggest that time itself might be an emergent property, rather than a fundamental one. One of the most famous challenges to our understanding of time in quantum mechanics comes from the Wheeler-DeWitt equation, which describes the wave function of the entire universe. This equation is time-independent, meaning it does not contain the variable of time. This has led some physicists to propose that at the most fundamental level, the universe is timeless, and that our perception of time emerges from the complex interactions of quantum systems. This idea of emergent time is a profound departure from our intuitive understanding. It suggests that time is not a fundamental building block of reality, but rather a consequence of the way we, as macroscopic observers, interact with the quantum world. Our perception of a flowing river of time might be an illusion, a useful but ultimately incomplete way of making sense of a timeless quantum reality. Another fascinating aspect of time in the quantum realm is the concept of quantum entanglement. When two particles are entangled, their fates are linked no matter how far apart they are. A measurement on one particle instantaneously affects the other, a phenomenon Einstein famously called spooky action at a distance. This instantaneous connection seems to defy the speed of light, which is supposed to be the ultimate speed limit in the universe. While entanglement does not allow for faster-than-light communication, it does challenge our classical notions of space and time, suggesting a deeper, more interconnected reality than we can directly perceive. Furthermore, the quantum world is filled with probabilities and uncertainties. Particles do not have definite properties until they are measured, and their behavior is governed by wave functions that describe the probability of finding them in a particular state. This probabilistic nature of reality at the quantum level might be connected to the arrow of time. Some theories propose that the arrow of time arises from the continuous process of quantum measurement, where the universe transitions from a state of many possibilities to a single definite outcome. These quantum insights into the nature of time are still the subject of intense research and debate. They push the boundaries of our understanding and force us to confront the limitations of our classical intuition. The calm cosmos, with its silent quantum depths, invites us to contemplate these profound mysteries, to question our most basic assumptions about reality, and to embrace the uncertainty that lies at the heart of the universe. The journey to understand time is not just a scientific one, it is also a deeply philosophical one. For centuries, philosophers have grappled with the nature of time, its relationship to consciousness, and its implications for human existence. These philosophical inquiries offer a rich tapestry of ideas that complement and enrich our scientific understanding. One of the most enduring philosophical debates about time is the A theory versus the B theory. The A theory, which aligns with our intuitive experience, posits that time is a real, flowing entity, and that the past, present, and future are distinct and have different ontological statuses. The present is real, the past is no longer real, and the future is not yet real. This view embraces the dynamic, ever-changing nature of time. In contrast, the B theory, which is more in line with the block universe concept from physics, argues that all moments in time are equally real. The past, present, and future are just different points in a four-dimensional space-time, and our perception of time's flow is a subjective illusion. In this view, there is no objective now, and the distinction between past, present, and future is a product of our consciousness. These two perspectives offer vastly different ways of understanding our place in the universe. The A theory provides a framework for concepts like free will and personal growth, as the future is seen as open and unwritten. The B theory, on the other hand, offers a more deterministic view, where all of a person's life, from birth to death, is already laid out in space-time. However, it also offers a sense of cosmic unity, where all moments are interconnected and equally part of the grand tapestry of existence. Another profound philosophical question is the relationship between time and consciousness. Is our experience of time a direct perception of an external reality, or is it a construct of our minds? Some philosophers, like Immanuel Kant, argue that time is a fundamental structure of our consciousness, a lens through which we organize our experiences. In this view, we do not perceive time as it is in itself, but rather as it is shaped by our cognitive faculties. This idea has fascinating implications. If time is a product of our minds, does that mean that beings with different cognitive structures would experience time differently? Could there be forms of consciousness that do not experience time as a linear flow? These questions challenge us to consider the diversity of possible experiences and to recognize the limitations of our own human perspective. The calm cosmos, in its silent, contemplative vastness, provides the perfect backdrop for these philosophical inquiries. It invites us to look beyond the equations and the data to the deeper questions of meaning and existence that lie at the heart of our quest to understand time. It reminds us that science and philosophy are not separate endeavours, but two sides of the same coin, both essential for a complete and holistic understanding of the universe. As we delve deeper into the mystery of time, we encounter the concept of the arrow of time, the observation that time always seems to move in one direction, from past to future. This unidirectional flow is one of the most fundamental and yet least understood aspects of our universe. Why do we remember the past but not the future? Why do eggs break but not unbreak? The arrow of time is responsible for the asymmetry we observe in the world around us, and its origin is a profound puzzle. One of the leading explanations for the arrow of time is rooted in the second law of thermodynamics, which states that the total entropy, or disorder, of an isolated system can only increase over time. The universe, as a whole, is believed to have started in a state of very low entropy at the Big Bang, and it has been evolving towards a state of higher entropy ever since. This continuous increase in disorder is what gives time its direction. Imagine a room with a box of gas in one corner. If you open the box, the gas molecules will spread out to fill the entire room, a state of higher entropy. It is incredibly unlikely that the gas molecules will spontaneously gather back into the box, a state of lower entropy. This is a simple analogy for the arrow of time. The universe is constantly moving from more ordered states to more disordered ones, and this is what we perceive as the forward flow of time. However, this explanation raises its own set of questions. Why was the universe in such a low entropy state to begin with? This is a major puzzle in cosmology, and there are various theories that attempt to explain it, from the inflationary model of the early universe to more speculative ideas about the nature of the Big Bang itself. Another perspective on the arrow of time comes from cosmology and the expansion of the universe. The expansion of space itself provides a clear directionality to the evolution of the cosmos. As the universe expands, galaxies move further apart, and the overall density and temperature decrease. This cosmic evolution provides a clear arrow of time on the larger scales. There is also a psychological arrow of time, which is our subjective experience of time's passage. We remember the past and anticipate the future, and this creates a clear directionality in our conscious experience. This psychological arrow is likely linked to the thermodynamic arrow, as our brains are physical systems that are subject to the laws of thermodynamics. The process of forming memories, for instance, is an irreversible process that increases entropy. Finally, there is the radiation arrow of time, which is the observation that we see light coming from distant stars, but we do not see light converging on them. This is because the universe is filled with sources of radiation that emit light outwards, but not sinks that absorb it from all directions. This asymmetry is also linked to the low entropy state of the early universe. The calm cosmos, with its ever-expanding horizons and its silent, irreversible processes, is a constant reminder of the arrow of time. It invites us to contemplate the deep connection between the microscopic world of particles and the macroscopic world of our experience, and to marvel at the intricate web of causality that weaves the fabric of our reality. Our journey into the nature of time would be incomplete without exploring its most extreme manifestations, the points in the universe where our current understanding of physics breaks down. These are the singularities, the infinitely dense and hot points that are thought to exist at the center of black holes and at the very beginning of the universe, the Big Bang. In these extreme environments, the fabric of space-time is so severely warped that the concepts of space and time as we know them lose their meaning. The equations of general relativity, which so accurately describe gravity in our everyday experience, predict that at a singularity, the curvature of space-time becomes infinite. This is a clear indication that our current theories are incomplete, and that we need a new theory, a theory of quantum gravity, to understand what happens in these extreme realms. What does a singularity tell us about the nature of time? At the Big Bang singularity, it is believed that time itself began. There was no before the Big Bang because the concept of time did not exist. This is a mind-bending idea as it challenges our intuitive notion of a timeline that stretches infinitely into the past. It suggests that time, like space, had a beginning, and that the universe emerged from a state of timelessness. Similarly, at the singularity of a black hole, time is thought to end for any object that crosses the event horizon. As an object approaches the singularity, the tidal forces become infinitely strong, and the object is stretched and squeezed out of existence. According to general relativity, time itself comes to a halt at the singularity. This is another point where our current understanding of physics fails, and where a theory of quantum gravity is needed to provide a more complete picture. Some theories of quantum gravity, such as string theory and loop quantum gravity, offer tantalizing glimpses into what might happen at these singularities. String theory, for instance, suggests that the fundamental constituents of the universe are not point-like particles, but tiny, vibrating strings. In this framework, the Big Bang might not have been a singularity in the traditional sense, but rather a transition from a previous phase of the universe, a pre-Big Bang era. This would mean that time did not begin at the Big Bang, but has existed in some form for eternity. Loop quantum gravity, on the other hand, proposes that space-time itself is quantized, made up of discrete, indivisible units. In this view, the Big Bang singularity is replaced by a big bounce, where a previous universe collapsed and then bounced back to form our own. This cyclic model of the universe also suggests that time is eternal, with no beginning and no end. These are still speculative ideas, but they offer a fascinating glimpse into the frontiers of our scientific understanding. They remind us that the calm cosmos, with its silent, enigmatic black holes and its explosive, creative Big Bang, is a laboratory for exploring the most fundamental questions about the nature of time and existence. It invites us to embrace the unknown, to challenge our preconceived notions, and to continue our quest for a deeper understanding of the universe. As we've seen, our understanding of time is a rich tapestry woven from the threads of physics, philosophy, and cosmology. It is a concept that is both deeply familiar and profoundly mysterious, a constant companion in our lives and yet an elusive enigma that slips through our fingers whenever we try to grasp it. So, what is time, really? Perhaps there is no single simple answer. Time may be a fundamental dimension of the universe, a flowing river that carries us from the past to the future. Or it may be an emergent property of a timeless quantum reality, a useful illusion created by our macroscopic minds. It may be absolute and universal, or it may be relative and observer-dependent. It may have had a beginning at the Big Bang, or it may be eternal, with no beginning and no end. The beauty of this question lies not in finding a definitive answer, but in the journey of exploration itself. The quest to understand time has driven some of the greatest scientific and philosophical achievements in human history, and it continues to inspire us to push the boundaries of our knowledge. It is a testament to our innate curiosity, our desire to understand our place in the cosmos, and our capacity for wonder. In the calm cosmos, as we gaze upon the ancient light of distant stars, we are reminded of the vastness of time and the shortness of our own lives. This can be a humbling experience, but it can also be an empowering one. It reminds us to cherish the present moment, to live our lives to the fullest, and to appreciate the precious gift of consciousness that allows us to contemplate these profound mysteries. Perhaps the true nature of time is not something that can be captured in an equation or a philosophical treatise. Perhaps it is something that can only be experienced in the quiet moments of reflection, in the joyful moments of connection, and in the awe-inspiring moments of wonder. The calm cosmos, in its silent, timeless beauty, invites us to embrace this experiential understanding of time, to find meaning not in the answers, but in the questions themselves. As we conclude our journey into the heart of time, we're left with a sense of profound humility and a renewed sense of wonder. The universe is a vast and mysterious place, and our understanding of it is still in its infancy. But with every new discovery, with every new idea, we come a little closer to unravelling its secrets. And in this quest for knowledge, we also come a little closer to understanding ourselves. May your thoughts drift gently as you ponder the calm cosmos and the endless, enigmatic river of time. Our perception of time is not just a matter of physics, it is deeply intertwined with our psychology and consciousness. The way we experience time can be highly subjective, influenced by our emotions, attention, and the activities we are engaged in. This psychological arrow of time often deviates from the objective, physical flow, creating a rich and complex inner world. Consider how time seems to speed up when we are enjoying ourselves, and slow down when we are bored or anxious. A thrilling adventure might feel like it passes in a flash, while a few minutes of waiting can stretch into an eternity. This phenomenon, known as chronostasis, or the stopped clock illusion, highlights how our brains actively construct our experience of time rather than passively receiving it. Our brains are constantly processing information, and the perception of time is a result of this complex neural activity. Different brain regions are involved in various aspects of time perception, from the precise timing of movements to the broader sense of duration. For instance, the cerebellum is crucial for motor timing, while the basal ganglia and prefrontal cortex play roles in estimating longer durations. Memory also plays a significant role in our subjective experience of time. We tend to remember novel and emotionally charged events more vividly, and these memories can make periods of our lives seem longer in retrospect. Conversely, routine periods, though they may have lasted for years, can feel compressed when we look back, as there are fewer distinct memories to mark their passage. This subjective nature of time raises fascinating questions about the relationship between our inner world and the external reality. Is there a universal, objective time that exists independently of our minds, or is time fundamentally a product of consciousness? While physics describes time as a dimension of space-time, our lived experience of time is undeniably shaped by our internal states. Furthermore, the concept of present moment is also a psychological construct. What exactly constitutes the now? Is it an infinitely small point between the past and the future, or does it have a duration? Psychologists and neuroscientists suggest that our present is not a single instant but a brief window of perception, a specious present, where sensory information is integrated and interpreted. This allows us to perceive events as continuous, rather than as a series of disconnected snapshots. The calm cosmos, with its vast stretches of cosmic time, invites us to reflect on our own fleeting yet profound experience of time. It reminds us that while the universe operates on scales far beyond our comprehension, our individual perception of time is a unique and intricate dance between the objective flow of the cosmos and the subjective workings of our minds. This interplay adds another layer of mystery to the question of what time truly is, urging us to look both outward into the universe and inward into the depths of our own consciousness. The intricate dance between time and gravity is one of the most profound insights offered by Einstein's theory of general relativity. It reveals that time is not a separate, unchanging backdrop against which events unfold, but an active participant in the cosmic drama, intimately linked to the distribution of mass and energy in the universe. This connection leads to fascinating phenomena that challenge our everyday intuition. One of the most striking consequences of this relationship is gravitational time dilation. This means that time passes more slowly in stronger gravitational fields. For example, a clock at the top of a mountain will tick slightly faster than a clock at sea level, because the gravitational pull is weaker at higher altitudes. While this difference is minuscule in our daily lives, it becomes significant in extreme gravitational environments, such as near black holes or massive stars. Imagine an astronaut orbiting a black hole. For the astronaut, time would pass normally. But for an observer far away from the black hole, the astronaut's clock would appear to tick much slower. If the astronaut were to approach the event horizon, the boundary beyond which nothing, not even light, can escape, time would appear to slow down almost infinitely from the perspective of the distant observer. The astronaut would appear to freeze in time, never quite crossing the event horizon. This phenomenon is not just a theoretical construct, it has practical applications. The GPS satellites that guide our navigation systems orbit Earth at high altitudes, where gravity is slightly weaker than on the surface. Due to gravitational time dilation, their clocks run slightly faster than clocks on Earth. If these relativistic effects were not accounted for, GPS systems would accumulate errors of several kilometers per day, rendering them useless. This real-world application underscores the profound accuracy and importance of Einstein's theories. Furthermore, the expansion of the universe itself provides another cosmic clock. As space expands, the light from distant galaxies is stretched, causing its wavelength to increase, a phenomenon known as cosmological redshift. This redshift is a direct measure of how much the universe has expanded since the light was emitted, providing a way to look back in time and study the early universe. The relationship between time and gravity also plays a crucial role in the ultimate fate of the universe. If the universe contains enough mass and energy, its gravitational pull could eventually overcome the expansion, causing it to contract in a big crunch, where time might reverse or cease to exist. Conversely, if the universe continues to expand indefinitely, driven by dark energy, it could lead to a big freeze or big rip, where time continues, but the universe becomes increasingly dilute and empty. These cosmic scenarios highlight that time is not merely a passive observer of the universe's evolution, but an active participant, its flow and very existence intertwined with the gravitational forces that shape the cosmos. The calm cosmos, in its silent gravitational embrace, reveals that time is a dynamic and flexible entity, its rhythm dictated by the very fabric of space-time. It invites us to ponder the profound implications of a universe where time itself is a cosmic variable, constantly shifting and bending under the influence of gravity. The arrow of time, the undeniable directionality of time from past to future, is one of the most fundamental and yet perplexing aspects of our universe. Why do we remember yesterday but not tomorrow? Why do broken cups not spontaneously reassemble? This asymmetry is deeply rooted in the concept of entropy, a measure of disorder or randomness in a system. The second law of thermodynamics states that the total entropy of an isolated system can only increase over time. In simpler terms, things tend to move from order to disorder. A tidy room, if left unattended, will naturally become messy. A drop of ink in water will spread out, not gather back into a concentrated drop. This universal tendency towards increasing disorder is what gives time its forward momentum. At the Big Bang, the universe is believed to have been in an incredibly low entropy state, a state of extreme order and uniformity. Since then, as the universe has expanded and evolved, its entropy has been continuously increasing. This cosmic march towards greater disorder is what we perceive as the passage of time. The universe is constantly moving from more organized configurations to less organized ones, and this irreversible process defines the arrow of time. This thermodynamic arrow of time is pervasive. It governs everything from the decay of radioactive elements to the aging of living organisms. Our own biological processes, from metabolism to memory formation, are all subject to the relentless increase in entropy. The act of remembering, for instance, involves creating new, more disordered neural connections, solidifying the past and distinguishing it from the uncertain future. However, the connection between entropy and time raises a profound question. Why did the universe start in such a low entropy state? This is a major unsolved problem in cosmology. If the universe were truly isolated, it should have started in a high entropy state, or at least a more probable one. The fact that it began in such an improbable, highly ordered state is a mystery that continues to challenge physicists. Some theories propose that the low entropy of the early universe is a consequence of cosmic inflation, a period of extremely rapid expansion immediately after the Big Bang. Inflation could have smoothed out initial irregularities and stretched the universe to a vast size, effectively diluting any initial disorder and setting the stage for the subsequent increase in entropy. Other more speculative ideas suggest that our universe might be part of a larger multiverse, where different universes have different initial conditions and different arrows of time. In this scenario, our universe simply happens to be one where the arrow of time is clearly defined, allowing for the emergence of complex structures and life. Regardless of its ultimate origin, the thermodynamic arrow of time provides a powerful framework for understanding the unidirectional flow of our experience. It reminds us that the universe is not static, but a dynamic system constantly evolving towards a state of greater disorder. The calm cosmos, in its silent entropic march, invites us to contemplate the profound implications of this fundamental asymmetry and to find a sense of peace in the irreversible flow of time. The allure of time travel has captivated human imagination for centuries, giving rise to countless stories, theories, and paradoxes. While it remains firmly in the realm of science fiction for now, the very concept of traversing time forces us to confront the fundamental nature of causality and the potential flexibility of the temporal dimension. From a scientific perspective, Einstein's theory of general relativity does not explicitly forbid time travel. In fact, some solutions to Einstein's equations, such as those involving wormholes or rapidly rotating black holes, theoretically allow for the possibility of closed time-like curves, CTCs, which are paths through space-time that return to their starting point. If CTCs were traversable, they could in principle allow for travel into the past or future. However, the practical challenges of creating and stabilizing such structures are immense, requiring exotic matter with negative energy density, which has never been observed. Even if such structures could be created, the paradoxes they present are formidable. The most famous of these is the grandfather paradox. If you travel back in time and prevent your grandfather from meeting your grandmother, you would never be born, and thus could not travel back in time to prevent their meeting in the first place. This creates a logical inconsistency that challenges the very fabric of causality. Various solutions have been proposed to resolve these paradoxes. One is the Novikov self-consistency principle, which suggests that if time travel to the past were possible, any actions taken by the time traveller would already be part of history, making it impossible to change past events. In this view, the past is immutable, and any attempt to alter it would simply lead to the outcome that was always destined to happen. Another approach is the many worlds interpretation of quantum mechanics, which we touched upon earlier. If every quantum event causes the universe to branch into multiple parallel universes, then travelling to the past and making a change would simply lead you to a different branch of the multiverse, leaving your original timeline unaffected. In this scenario, there is no single, fixed past to paradoxically alter. Then there's the idea of a mutable past, where changes are possible, but the consequences are unpredictable and could lead to entirely new timelines or even the erasure of the time traveller's original existence. This is the realm of pure speculation, but it highlights the profound implications of tampering with the temporal dimension. Time travel to the future, on the other hand, is already a proven phenomenon, albeit on a very small scale. Due to time dilation, astronauts on the International Space Station age fractionally slower than people on Earth because of their high speed and slightly weaker gravitational field. While this is not the dramatic leap into the future depicted in science fiction, it demonstrates that time is indeed relative and can be experienced differently. The calm cosmos, with its vast stretches of space-time, holds these theoretical possibilities and paradoxes within its silent embrace. It invites us to ponder the limits of our understanding, the intricate web of cause and effect, and the potential for realities far stranger than our current comprehension allows. The contemplation of time travel, even if purely hypothetical, deepens our appreciation for the delicate balance of causality that governs our universe and the profound mystery of time itself. Our understanding of time is deeply intertwined with the cosmological models that describe the universe as a whole. Different theories about the universe's origin, evolution, and ultimate fate offer varying perspectives on the nature and role of time. These grand narratives of the cosmos provide a canvas upon which the intricate dance of time unfolds. In the standard Big Bang model, time is generally understood to have begun with the universe itself, approximately 13.8 billion years ago. Before the Big Bang, the concept of time, as we understand it, is thought to be meaningless. This implies a finite past for time, a starting point from which all events have unfolded. This perspective is deeply embedded in our scientific understanding and shapes our view of causality and cosmic history. However, some alternative cosmological models challenge this notion of a singular beginning for time. Cyclic universe models, for instance, propose that the universe undergoes an endless series of expansions and contractions, with each big crunch leading to a new Big Bang. In such models, time would be eternal, without a true beginning or end, continuously flowing through successive cosmic cycles. This offers a more cyclical view of time, where the past and future are not merely linear but part of an endless cosmic rhythm. Another intriguing concept is the eternal inflation model, which suggests that inflation, the rapid expansion of the early universe, never truly ends in all regions. Instead, it continues indefinitely in some parts, constantly spawning new bubble universes. In this multiverse scenario, time within each bubble universe might have a beginning, but the overarching time of the inflating multiverse would be eternal. This presents a hierarchical view of time, with local temporal flows embedded within a larger unending cosmic process. These cosmological models not only describe the large-scale structure and evolution of the universe, but also offer profound insights into the nature of time itself. They force us to consider whether time is an intrinsic property of the universe, a fundamental dimension that exists independently of matter and energy, or whether it is an emergent phenomenon, a consequence of the universe's dynamic processes. The calm cosmos, in its silent, evolving grandeur, presents these diverse temporal landscapes. It invites us to contemplate the possibility of multiple temporal realities, each governed by the specific conditions of its cosmic environment. The exploration of these cosmological models deepens our appreciation for the multifaceted nature of time, reminding us that our intuitive understanding is but one small facet of a much larger, more complex cosmic truth. The quest to unify general relativity and quantum mechanics, known as quantum gravity, presents one of the most significant challenges to our understanding of time. In the realm where the very small meets the very large, our conventional notions of time begin to fray, and new, often counterintuitive, ideas emerge. General relativity describes gravity as the curvature of space-time, a smooth and continuous fabric. Quantum mechanics, on the other hand, suggests that everything, including space and time, should ultimately be quantized, meaning it's made up of discrete indivisible units. Reconciling these two perspectives is a monumental task, and the resulting theories often propose a radically different picture of time. In some approaches to quantum gravity, such as loop quantum gravity, space-time itself is thought to be granular, composed of tiny loops or networks. In this framework, time might not be a fundamental background against which events unfold, but rather an emergent property arising from the relationships and interactions between these fundamental quantum units. This means that time, as we experience it, might not exist at the most fundamental level of reality. Another prominent theory, string theory, posits that the fundamental constituents of the universe are not point-like particles, but tiny, vibrating strings. In some versions of string theory, the concept of time can be more complex, with extra dimensions that could potentially be curled up or hidden from our perception. This could lead to scenarios where time behaves differently at very small scales, or in different regions of the universe. One of the most perplexing aspects of quantum gravity is the Wheeler-DeWitt equation, which appears in canonical quantum gravity. This equation, when applied to the universe as a whole, is timeless. It does not contain a time variable, leading to the so-called problem of time in quantum gravity. If the fundamental equation describing the universe does not include time, then how does time emerge in our experience? Various interpretations and solutions have been proposed for the problem of time. Some suggest that time is indeed an illusion at the fundamental level, and our perception of its flow arises from the entanglement of quantum states, or from the way we coarse-grain information. Others argue that time is a relational concept, defined by the changes and correlations between physical degrees of freedom rather than an independent background. These theories, while highly speculative and still under development, push the boundaries of our understanding of time to its absolute limits. They suggest that time, far from being a simple linear progression, might be a complex emergent phenomenon, deeply intertwined with the very fabric of reality at its most fundamental level. The calm cosmos, in its silent quantum depths, invites us to contemplate these profound mysteries, to question our most basic assumptions about reality, and to embrace the uncertainty that lies at the heart of the universe's deepest secrets. The journey into the quantum nature of time is a testament to the human intellect's relentless pursuit of knowledge. It reminds us that the universe, at its core, might be far more alien and counterintuitive than our everyday experiences suggest. Yet, within this strangeness lies the potential for a deeper, more complete understanding of what time truly is, and how it shapes our existence within the grand cosmic tapestry of the cosmos. The relationship between time and consciousness is one of the most profound and enigmatic areas of inquiry. Is our experience of time merely a passive reception of an external reality, or does consciousness actively shape our perception of its flow? This question delves into the very heart of what it means to be a conscious being in a temporal universe. Philosophers and psychologists have long debated whether time is an objective feature of the universe or a subjective construct of the mind. Immanuel Kant, for instance, argued that time is not an empirical concept derived from experience, but rather a fundamental intuition, a necessary form of our inner sense, through which we organize our perceptions. In this view, time is a lens through which we experience the world, rather than an independent entity existing outside of us. Our subjective experience of time is remarkably flexible. As we discussed earlier, time can seem to speed up or slow down depending on our emotional state, attention, and engagement with an activity. When we are deeply engrossed in a task, hours can feel like minutes. Conversely, moments of boredom or anxiety can stretch into what feels like an eternity. This elasticity of perceived time suggests that our consciousness plays a crucial role in its unfolding. Neuroscientific research has begun to shed light on the neural mechanisms underlying time perception. Different brain regions and networks are involved in processing temporal information, from the precise timing of milliseconds to the broader sense of duration over hours or days. The brain does not have a single time organ, but rather integrates information from various sensory modalities and internal clocks to construct our coherent experience of time. Furthermore, the concept of the present moment is not as straightforward as it seems. While we intuitively feel that we live in a continuous now, neuroscientists suggest that our conscious present is not an infinitely thin slice of time, but rather a brief window of perception, a specious present lasting a few seconds. Within this window, our brains integrate sensory information and create a coherent narrative of reality. This allows us to perceive motion, speech, and music as continuous flows rather than as discrete, disconnected snapshots. This raises a fascinating question. If our conscious present has a duration, what happens to the information outside of that window? Does it simply cease to exist for us, or is it integrated into our memories and expectations? The dynamic interplay between memory, attention, and anticipation constantly shapes our experience of the present, blurring the lines between past, present, and future. The calm cosmos, with its silent, timeless expanse, invites us to ponder the profound connection between time and consciousness. It reminds us that our internal world is not merely a passive reflection of external reality, but an active participant in its construction. The journey to understand time is, in many ways, a journey into the depths of our own minds, revealing the intricate ways in which our consciousness shapes the very fabric of our temporal existence. The question of whether time had a beginning and if it will have an end is one of the most profound and enduring mysteries in cosmology and philosophy. Our intuitive understanding suggests a clear start and finish, but the universe, in its vastness, often defies such simple notions. From a scientific perspective, the prevailing Big Bang model suggests that time, as we understand it, began approximately 13.8 billion years ago with the universe itself. Before this moment, the concept of time is thought to be meaningless, as there was no space-time to measure its passage. This implies a finite past for time, a cosmic clock that started ticking at the moment of creation. However, this idea of a singular beginning for time is not without its challenges and alternative theories. Some quantum gravity theories, such as loop quantum gravity, propose a Big Bounce scenario, where the Big Bang was not the absolute beginning, but rather a transition from a previous contracting universe. In this cyclic model, time would be eternal, continuously flowing through an endless series of cosmic expansions and contractions, with no true beginning or end. Philosophically, the concept of an absolute beginning of time raises deep questions. If time began, what caused it to begin? And if there was no time before the Big Bang, then how can we speak of a cause in the traditional sense, as causality itself implies a temporal sequence? These are the kinds of paradoxes that emerge when we push our understanding to its limits. Similarly, the question of time's end is a subject of intense speculation, closely tied to the ultimate fate of the universe. If the universe continues to expand indefinitely, driven by dark energy, it could lead to a big freeze or heat death, where the universe becomes increasingly cold, dilute, and empty. In this scenario, time would continue, but all processes would eventually cease, leading to a state of maximum entropy, where nothing interesting ever happens again. It would be an end to events, rather than an end to time itself. Another possibility is the Big Rip, where the accelerating expansion of the universe becomes so extreme that it eventually tears apart all structures, from galaxies to atoms, and even space-time itself. In this catastrophic scenario, time might literally cease to exist as the very fabric of reality unravels. Conversely, if the universe were to eventually contract in a big crunch, time might reverse its flow as the universe collapses back into a singularity. This idea, while intriguing, faces significant theoretical hurdles and is not currently favoured by observational evidence. Beyond these physical scenarios, philosophical considerations also play a role. Some philosophers argue that time is fundamentally tied to change. If there were no change in the universe, would time still exist? If the universe reached a state of absolute equilibrium, where nothing ever happened, would time effectively end for all practical purposes, even if it continued to flow theoretically? The calm cosmos, in its silent, evolving grandeur, presents these profound questions about the beginning and end of time. It invites us to contemplate the possibility of an eternal universe, a universe with a finite lifespan, or even a universe where time itself is an emergent property that can begin and end. The exploration of these ideas pushes the boundaries of our scientific and philosophical understanding, reminding us that the universe holds secrets far grander and more complex than we can fully grasp. In the bizarre and counterintuitive world of quantum mechanics, our classical understanding of time often breaks down, leading to profound questions about its very existence at the most fundamental level. Here, particles can exist in multiple states simultaneously, and their properties are not fixed until they are observed, challenging our notions of causality and the flow of events. One of the most perplexing aspects of time in quantum mechanics is the absence of a clear time operator in the standard formulation. Unlike position or momentum, there isn't a straightforward quantum mechanical operator for time. This has led some physicists to suggest that time might not be a fundamental observable in the same way as other physical quantities, but rather an emergent property of the quantum world. The famous Wheeler-DeWitt equation, a cornerstone of canonical quantum gravity, describes the wave function of the entire universe. Strikingly, this equation is timeless. It does not contain a time variable. This problem of time in quantum gravity implies that at the most fundamental level, the universe might be static and timeless, and our perception of time's flow could be an illusion, arising from the entanglement of quantum states or from the way we coarse-grain information. Consider the concept of quantum superposition, where a particle can exist in multiple states at once until it is measured. This means that a particle can be in two places at the same time or have two different energies simultaneously. When we make a measurement, the superposition collapses into a single definite state. This act of measurement seems to introduce a directionality, a now, into the quantum world, which might be linked to the emergence of our perceived arrow of time. Furthermore, quantum entanglement, where two particles become linked in such a way that the state of one instantaneously influences the state of the other, regardless of distance, also challenges our classical notions of time. While entanglement does not allow for faster-than-light communication, it suggests a deeper, non-local connection between events that transcends our ordinary understanding of temporal separation. The probabilistic nature of quantum mechanics also plays a role. Unlike classical physics, where events are deterministic, quantum events are inherently probabilistic. We can only predict the likelihood of a particular outcome. This inherent uncertainty at the quantum level might be related to the open-endedness of the future and the irreversible nature of the past. The unfolding of quantum probabilities into definite outcomes could be seen as a fundamental process that drives the arrow of time. These quantum insights suggest that time, far from being a simple linear progression, might be a complex emergent phenomenon, deeply intertwined with the very fabric of reality at its most fundamental level. It challenges us to rethink our most basic assumptions about what time is and how it shapes our existence within the grand cosmic tapestry. The calm cosmos, in its silent quantum depths, invites us to contemplate these profound mysteries, to question our most basic assumptions about reality, and to embrace the uncertainty that lies at the heart of the universe's deepest secrets. Our personal experience of time is inextricably linked to memory. It is through our ability to recall past events and anticipate future ones that we construct a coherent narrative of our lives and navigate the world around us. This intimate connection between time and memory reveals much about the subjective nature of our temporal perception. Memory is not a perfect recording device. It is a reconstructive process. Each time we recall a memory, we are not simply replaying a fixed recording, but actively rebuilding it, often influenced by our current state, emotions, and new information. This dynamic nature of memory means that our perception of the past is not static but can shift and evolve over time. The way our memories are organized also influences our experience of time. Episodic memories, which are memories of specific events and experiences, are often tied to a particular time and place. Semantic memories, on the other hand, are memories of facts and general knowledge, and are less tied to a specific temporal context. The interplay between these different types of memory contributes to our overall sense of time and continuity. Furthermore, the emotional content of our memories can significantly impact our perception of duration. Traumatic events, for instance, can feel like they happened just yesterday, even if they occurred years ago due to their intense emotional imprint. Conversely, periods of routine or low emotional intensity can feel compressed in retrospect, as there are fewer distinct emotional markers to anchor them in time. Our ability to mentally time travel, to revisit past events in our minds, and to imagine future scenarios is a unique human capacity. This capacity for mental time travel is closely linked to our sense of self and our ability to plan and make decisions. It allows us to learn from past mistakes, to anticipate future challenges, and to set goals for ourselves. However, this mental time travel is not without its limitations. Our memories can be fallible, and our predictions about the future are often uncertain. This inherent uncertainty in our temporal projections highlights the probabilistic nature of existence, and the constant interplay between what has been, what is, and what might be. The calm cosmos, with its vast stretches of cosmic history, invites us to reflect on our own personal timelines and the role of memory in shaping our experience of time. It reminds us that while the universe operates on scales far beyond our comprehension, our individual perception of time is a unique and intricate dance between the objective flow of the cosmos and the subjective workings of our minds. This interplay adds another layer of mystery to the question of what time truly is, urging us to look both outward into the universe and inward into the depths of our own consciousness. Beyond the realms of physics and philosophy, time manifests itself in profound ways within biological systems, shaping life from its simplest forms to the most complex. The very essence of life is intrinsically linked to time, from the rhythmic ticking of cellular clocks to the grand sweep of evolution over billions of years. At the cellular level, organisms possess intricate biological clocks, known as circadian rhythms, which regulate various physiological processes over approximately a 24-hour cycle. These internal clocks, influenced by external cues like light and darkness, govern sleep-wake cycles, hormone release, body temperature, and many other vital functions. They are a testament to how life has adapted to the temporal rhythms of our planet, synchronizing its internal processes with the external world. On a larger scale, the passage of time is evident in the processes of growth, aging, and death. From the moment of conception, organisms embark on a temporal journey, developing, maturing, and eventually succumbing to the relentless march of time. Aging, a complex biological process, involves the gradual accumulation of damage at the cellular and molecular levels, leading to a decline in function and an increased susceptibility to disease. While science is making strides in understanding and potentially mitigating aspects of aging, the fundamental unidirectional flow of biological time remains a profound reality. Evolution, the grand narrative of life on Earth, unfolds over vast stretches of geological time. The diversity of species we observe today is the result of billions of years of natural selection, adaptation, and genetic change. Each species, each individual, is a product of this immense temporal process, carrying within its DNA the echoes of countless generations that have come before. The fossil record, a silent testament to deep time, reveals the slow, incremental changes that have shaped life on our planet. The concept of time in biology also extends to the intricate timing of developmental processes. From the precise sequence of gene expression that guides the formation of an embryo, to the coordinated firing of neurons that enables thought, biological systems are exquisitely tuned to temporal cues. Disruptions in this delicate timing can lead to developmental abnormalities or neurological disorders, highlighting the critical role of time in the proper functioning of living organisms. Furthermore, the very definition of life often involves a temporal component. Living systems are characterized by their ability to maintain themselves, grow, and reproduce, all of which are processes that unfold over time. They are dynamic, far from equilibrium systems that constantly exchange matter and energy with their environment, maintaining their internal order against the relentless tide of increasing entropy. The calm cosmos, with its silent ancient stars and its vibrant evolving planets, reminds us that time is not just a cosmic phenomenon, but an intimate part of our very being. It is the canvas upon which the story of life is painted. From the fleeting moments of a single cell to the grand epic of evolution, the exploration of time in biological systems deepens our appreciation for the intricate dance between the physical laws of the universe and the emergent properties of life, urging us to contemplate the profound temporal journey that defines our existence. Beyond the scientific and philosophical frameworks, our understanding and experience of time are profoundly shaped by culture, language, and individual perception. Time, in this sense, is not just a universal constant, but a deeply human construct, interpreted and lived in myriad ways across different societies and personal realities. Consider how different languages conceptualize time. Some languages, like English, often use spatial metaphors for time, speaking of long or short periods, or looking forward to the future and back to the past. Other languages might use different metaphors, or even perceive time as flowing in a direction contrary to our common understanding, such as from future to past. Cultural differences in time, perception are also evident in daily life. Some cultures operate on a more linear monochronic time system, where tasks are done sequentially and punctuality is highly valued. In contrast, polychronic cultures often prioritize relationships and flexibility, engaging in multiple tasks simultaneously, and viewing time as more fluid and less rigidly structured. These cultural nuances highlight that our experience of time is not solely dictated by universal physical laws, but is also a product of our social environment and learned behaviors. Furthermore, individual differences in time perception are common. Some people are naturally more future-oriented, constantly planning and anticipating what's next. Others might be more present-oriented, focusing on the immediate moment, or past-oriented, dwelling on memories and historical events. These temporal orientations can influence decision-making, emotional well-being, and overall life satisfaction. The concept of kairos in ancient Greek philosophy offers another perspective. While chronos refers to chronological sequential time, kairos denotes a propitious moment, a qualitative sense of time that is opportune or critical. This distinction emphasizes that not all moments are equal. Some carry a special significance or urgency, demanding a different kind of attention and action. This qualitative aspect of time is often overlooked in our modern, quantitative obsession with clocks and schedules. Religious and spiritual traditions also offer diverse interpretations of time. Many spiritual paths emphasize the importance of living in the present moment, transcending the linear flow of time to experience a deeper, more timeless reality. Concepts like eternity, reincarnation, and cyclical time are central to various belief systems, offering alternative frameworks for understanding our temporal existence. The calm cosmos, in its silent, timeless expanse, invites us to reflect on the diverse ways in which humanity has grappled with the enigma of time. It reminds us that our understanding is not monolithic, but a rich tapestry woven from scientific inquiry, philosophical contemplation, and cultural interpretation. This multifaceted view deepens our appreciation for the complexity of time, urging us to look beyond a single definition and embrace the myriad ways in which it shapes our lives and our perception of reality. The relationship between time and information is a fascinating area of study that bridges physics, computer science, and philosophy. Information, in its broadest sense, can be thought of as the arrangement or organization of matter and energy. As the universe evolves through time, information is constantly being created, processed, and in some cases lost or transformed. From a thermodynamic perspective, the arrow of time is intimately linked to the increase of entropy, which can also be understood as an increase in disorder or a decrease in accessible information. As a system becomes more disordered, the information about its initial state becomes increasingly difficult to retrieve. For example, when a glass breaks, the information about its original ordered structure is not destroyed, but it becomes dispersed and practically irretrievable. This irreversible loss of accessible information is a hallmark of the passage of time. In the context of black holes, the concept of information becomes even more perplexing. According to classical general relativity, anything that falls into a black hole is lost forever, including all its information. This leads to the famous information paradox, as quantum mechanics suggests that information should never be truly destroyed. Various theories, such as string theory and the holographic principle, attempt to resolve this paradox by proposing mechanisms through which information might be preserved, perhaps encoded on the event horizon or in a higher dimension. The holographic principle, for instance, suggests that all the information contained within a volume of space can be encoded on its boundary, much like a hologram. If this principle applies to the universe, it implies a deep connection between space, time, and information, suggesting that our three-dimensional reality might be a projection from a two-dimensional surface. This radical idea challenges our fundamental understanding of reality and the role of information in its construction. Furthermore, the processing of information is a fundamental aspect of life and consciousness. Our brains are constantly receiving, processing, and storing information, and this dynamic interplay is what allows us to perceive and interact with the world. The speed at which our brains process information can influence our subjective experience of time, contributing to the feeling that time speeds up or slows down in different situations. In the digital age, the concept of information has taken on new dimensions. We are constantly generating and consuming vast amounts of data, and the speed at which this information travels and is processed has a profound impact on our lives. The rapid advancements in computing power and artificial intelligence are pushing the boundaries of what is possible, raising questions about the future of information and its relationship to time. The calm cosmos, with its silent, information-rich expanse, invites us to ponder the intricate dance between time and information. It reminds us that the universe is not just a collection of matter and energy, but a vast repository of information, constantly evolving and transforming. The exploration of this relationship deepens our appreciation for the fundamental role of information in shaping our reality and the relentless march of time that governs its unfolding. The ultimate fate of the universe is a grand cosmological question that directly impacts our understanding of time. Will time continue indefinitely, or will it eventually cease to have meaning as the cosmos reaches its final state? The various scenarios for the universe's end offer different perspectives on the future of time itself. The most widely accepted scenario, given current observations of dark energy, is the Big Freeze, or heat death. In this future, the universe continues to expand at an accelerating rate. Galaxies will drift so far apart that they become isolated islands in an ever larger, emptier cosmos. Stars will eventually burn out, black holes will evaporate through Hawking radiation, and matter will decay into a thin, cold soup of fundamental particles. In this state of maximum entropy, all thermodynamic processes will cease, and the universe will reach a state of absolute equilibrium. Time, in a sense, would continue to flow, but there would be no events, no change, and thus no meaningful passage of time from a practical perspective. It would be an end to activity rather than an end to time itself. Another, more dramatic possibility is the Big Rip. If dark energy's repulsive force continues to strengthen, it could eventually become so powerful that it overcomes all other forces, tearing apart galaxies, then stars and planets, then atoms, and finally even the fabric of space-time itself. In this catastrophic scenario, time would literally cease to exist as the very dimensions that define it are ripped apart. This would be a true end to time, a complete unravelling of the cosmic tapestry. Less favoured by current data, but still a theoretical possibility, is the Big Crunch. If the density of matter and energy in the universe were high enough, gravity could eventually halt the expansion and cause the universe to contract. Galaxies would rush back together, temperatures would rise, and the universe would collapse back into an infinitely hot, dense singularity, similar to the Big Bang. In this scenario, time might reverse its flow during the contraction phase, or it might simply cease to have meaning at the singularity, potentially leading to a new Big Bang in a cyclic universe. These cosmic fates highlight the profound connection between the evolution of the universe and the nature of time. Whether time continues indefinitely in a state of cosmic stillness, is violently torn apart, or reverses its flow, its destiny is inextricably linked to the grand narrative of the cosmos. The calm cosmos, in its silent, evolving grandeur, invites us to contemplate these ultimate possibilities, reminding us that our understanding of time is a journey that extends from the Big Bang to the farthest reaches of the universe's future. In philosophical discourse, the concept of timelessness offers a radical alternative to our everyday experience of time as a flowing entity. If time is not a fundamental aspect of reality, but rather an emergent property or an illusion, then what does it mean for existence to be timeless? This inquiry leads us to consider ideas of eternalism, where all moments in time are equally real and exist simultaneously. Eternalism, often associated with the B-theory of time, posits that the past, present, and future are not distinct in their reality. Instead, they are all equally existent, like different points on a spatial line. Our perception of time passing, of a now that moves, is seen as a subjective experience, a way our consciousness navigates this fixed four-dimensional block universe. In this view, events do not happen in time, they simply are at their respective temporal coordinates. This perspective has profound implications. If all moments are equally real, then the future is not something yet to be created, but something that already exists. This can be unsettling, as it seems to challenge the notion of free will and the idea that our choices genuinely shape what is to come. However, proponents of eternalism argue that our choices too are part of the fixed spacetime block, and our experience of making decisions is simply our consciousness unfolding along its predetermined path. Timelessness also appears in various spiritual and mystical traditions, where the ultimate reality is often described as being beyond time, eternal, and unchanging. In these contexts, transcending the linear flow of time is seen as a path to enlightenment or a deeper understanding of the divine. The now becomes an eternal present, where past and future converge, and all of existence is experienced as a single, unified whole. From a scientific standpoint, the timeless nature of the Wheeler-DeWitt equation in quantum gravity provides a tantalizing hint that timelessness might be a feature of reality at its most fundamental level. If the universe's most basic description does not include time, then its emergence in our macroscopic experience becomes a crucial puzzle. This could imply that time is a statistical phenomenon arising from the collective behavior of countless quantum events, or a consequence of the way we, as observers, interact with the universe. The calm cosmos, in its silent, unchanging depths, invites us to contemplate these radical notions of timelessness. It challenges our deeply ingrained assumptions about the nature of reality, and encourages us to consider that our linear experience of time might be just one way of perceiving a much grander, more complex, and ultimately timeless existence. This journey into timelessness is not about denying the reality of our lived experience, but about expanding our understanding of what time truly is, and how it fits into the vast, eternal tapestry of the universe. The subjective experience of time is a fascinating realm where physics, psychology, and philosophy converge. While objective time, as measured by clocks, flows uniformly, our internal perception of time can be remarkably fluid, stretching and compressing in response to our emotional states, attention, and the richness of our experiences. Consider the phenomenon of flow state, where an individual is completely immersed in an activity, losing all sense of time. Hours can pass in what feels like minutes, as the mind is fully engaged and self-consciousness fades. Conversely, during moments of boredom, anxiety, or anticipation, time can seem to drag, each second stretching into an eternity. This elasticity of perceived time highlights the active role our consciousness plays in constructing our temporal reality. Our brains are not passive receivers of time, they are active constructors. Neuroscientific research suggests that various brain regions, including the cerebellum, basal ganglia, and prefrontal cortex, are involved in different aspects of time perception, from precise millisecond timing to the estimation of longer durations. These neural networks integrate sensory information, memories, and emotional cues to create our coherent, albeit subjective, experience of time. The concept of the specious present further illustrates this subjective construction. Our conscious now is not an infinitely thin slice of time, but rather a brief window of perception, typically lasting a few seconds, within which sensory information is integrated and interpreted. This allows us to perceive continuous motion, speech, and music, rather than a series of disconnected snapshots. The duration of this specious present can vary depending on attention and cognitive load, further contributing to the flexibility of our perceived time. Memory plays a crucial role in shaping our subjective timeline. Novel and emotionally significant events tend to be remembered more vividly, and can make periods of our lives seem longer in retrospect. Conversely, routine or uneventful periods can feel compressed when we look back, as there are fewer distinct memories to mark their passage. This reconstructive nature of memory means that our personal history is not a fixed record, but a dynamic narrative constantly being re-edited by our present selves. Furthermore, our emotional state profoundly influences our time perception. Fear or excitement can make time seem to slow down, as our brains process information at an accelerated rate, creating a sense of hyper-awareness. This flashbulb memory effect, where vivid details of a traumatic or significant event are etched into our minds, often comes with a distorted sense of its duration. The calm cosmos, with its silent, unchanging expanse, invites us to reflect on the intricate dance between objective cosmic time and our subjective, conscious experience of it. It reminds us that while the universe operates on scales far beyond our comprehension, our individual perception of time is a unique and intricate dance between the objective flow of the cosmos and the subjective workings of our minds. This interplay adds another layer of mystery to the question of what time truly is, urging us to look both outward into the universe and inward into the depths of our own consciousness. The philosophy of time is a vast and ancient field, grappling with questions that predate modern science and continue to challenge our deepest assumptions. Beyond the scientific models, philosophical inquiry delves into the very essence of time, its relationship to existence, and its implications for human experience. One of the central debates in the philosophy of time revolves around whether time is a fundamental aspect of reality or an emergent property. Presentism, for instance, argues that only the present moment is real, the past is no longer real, and the future is not yet real. This view aligns with our intuitive experience of time as a flowing entity, where new moments are constantly coming into being and old ones are passing away. Presentism emphasizes the dynamic and ever-changing nature of reality, where events unfold sequentially. In contrast, eternalism, also known as the block universe theory, posits that all moments in time, past, present, and future, are equally real and exist simultaneously. In this view, time is like a spatial dimension, and all events are fixed points in a four-dimensional space-time block. Our perception of time passing, of a moving now, is seen as a subjective illusion, a way our consciousness navigates this fixed reality. Eternalism suggests a deterministic universe where everything that has happened, is happening, and will happen is already laid out. Another significant philosophical distinction is between substantivalism and relationalism. Substantivalism argues that space and time are independent entities, a kind of container in which events occur. Isaac Newton was a prominent substantivalist, believing in absolute space and absolute time that exist independently of any objects or events within them. In this view, time would still exist even if there were no events to mark its passage. Relationalism, on the other hand, posits that space and time are not independent entities, but are merely relations between objects and events. Gottfried Leibniz was a key proponent of relationalism, arguing that time is nothing more than the order of successive events. If there were no events, there would be no time. This view suggests that time is not a container but a description of the dynamic interactions within the universe. These philosophical positions have profound implications for our understanding of causality, free will, and the nature of reality itself. If time is a fixed block, does free will truly exist, or are our choices predetermined? If only the present is real, how do we account for the apparent influence of the past on the present, or our ability to plan for the future? The calm cosmos, in its silent philosophical depths, invites us to ponder these fundamental questions. It reminds us that our scientific models, while powerful, are often built upon underlying philosophical assumptions about the nature of time. By engaging with these philosophical debates, we deepen our appreciation for the complexity of time and the myriad ways in which it can be understood, pushing the boundaries of our intellectual inquiry beyond the purely empirical. The subjective experience of time is a fascinating realm where physics, psychology, and philosophy converge. While objective time, as measured by clocks, flows uniformly, our internal perception of time can be remarkably fluid, stretching and compressing in response to our emotional states, attention, and the richness of our experiences. Consider the phenomenon of flow state, where an individual is completely immersed in an activity, losing all sense of time. Hours can pass in what feels like minutes, as the mind is fully engaged and self-consciousness fades. Conversely, during moments of boredom, anxiety, or anticipation, time can seem to drag, each second stretching into an eternity. This elasticity of perceived time highlights the active role our consciousness plays in constructing our temporal reality. Our brains are not passive receivers of time, they are active constructors. Neuroscientific research suggests that various brain regions, including the cerebellum, basal ganglia, and prefrontal cortex, are involved in different aspects of time perception, from precise millisecond timing to the estimation of longer durations. These neural networks integrate sensory information, memories, and emotional cues to create our coherent, albeit subjective, experience of time. The concept of the specious present further illustrates this subjective construction. Our conscious now is not an infinitely thin slice of time, but rather a brief window of perception, typically lasting a few seconds, within which sensory information is integrated and interpreted. This allows us to perceive continuous motion, speech, and music, rather than a series of disconnected snapshots. The duration of this specious present can vary depending on attention and cognitive load, further contributing to the flexibility of our perceived time. Memory plays a crucial role in shaping our subjective timeline. Novel and emotionally significant events tend to be remembered more vividly and can make periods of our lives seem longer in retrospect. Conversely, routine or uneventful periods can feel compressed when we look back, as there are fewer distinct memories to mark their passage. This reconstructive nature of memory means that our personal history is not a fixed record, but a dynamic narrative constantly being re-edited by our present selves. Furthermore, our emotional state profoundly influences our time perception. Fear or excitement can make time seem to slow down, as our brains process information at an accelerated rate, creating a sense of hyper-awareness. This flashbulb memory effect, where vivid details of a traumatic or significant event are etched into our minds, often comes with a distorted sense of its duration. The calm cosmos, with its silent, unchanging expanse, invites us to reflect on the intricate dance between objective cosmic time and our subjective, conscious experience of it. It reminds us that while the universe operates on scales far beyond our comprehension, our individual perception of time is a unique and intricate dance between the objective flow of the cosmos and the subjective workings of our minds. This interplay adds another layer of mystery to the question of what time truly is, urging us to look both outward into the universe and inward into the depths of our own consciousness. As we conclude our journey through the calm cosmos and its profound exploration of time, we're left not with definitive answers, but with a deeper appreciation for the mystery itself. What is time, really? Perhaps it is not a single entity, but a multifaceted phenomenon, understood differently across the realms of physics, philosophy, biology, and our own subjective experience. Time, in its essence, remains an enigma. It is the canvas upon which the universe paints its grand narrative, from the Big Bang to its ultimate fate. It is the rhythm that governs the dance of particles in the quantum realm and the intricate processes of life on Earth. It is the subjective flow that shapes our memories, our perceptions, and our very consciousness. Perhaps the true meaning of time lies not in its precise scientific definition, but in its profound impact on our existence. It is time that allows for change, for growth, for evolution, and for the unfolding of possibilities. Without time, there would be no stories, no journeys, no learning, and no love. It is the medium through which we experience the richness and complexity of being. The calm cosmos, in its silent, timeless beauty, invites us to embrace this mystery. It reminds us that our quest for understanding is an ongoing journey, a continuous unfolding of knowledge and wonder. The questions we ask about time are, in many ways, questions about ourselves, our place in the universe, and the very nature of reality. May your thoughts drift gently as you ponder the calm cosmos and the endless, enigmatic river of time. May you find peace in its flow and wonder in its depths. For in the contemplation of time, we come closer to understanding the universe, and in understanding the universe, we come closer to understanding ourselves. The profound implications of time extend beyond its physical and psychological dimensions, deeply intertwining with the philosophical debate surrounding free will and determinism. If time is a fixed four-dimensional block, as eternalism suggests, does that mean our choices are predetermined? Or do we truly possess the freedom to shape our future? Determinism is the philosophical idea that all events, including human actions, are ultimately determined by causes external to the will. In a deterministic universe, every event is a necessary consequence of antecedent events and conditions. If the past, present, and future all exist simultaneously in a fixed space-time block, then it would seem that our future actions are already laid out, leaving no room for genuine choice. This perspective can be unsettling, as it appears to undermine our intuitive sense of agency and moral responsibility. If our decisions are merely the inevitable outcome of prior causes, then how can we be held accountable for our actions? The feeling of making a choice, of weighing options and deciding a course of action, would then be an illusion, a subjective experience that does not reflect an underlying reality. However, not all interpretations of time and determinism lead to such a bleak conclusion. Compatibilism, for instance, argues that free will and determinism are not necessarily mutually exclusive. It suggests that free will can exist even in a deterministic universe, as long as our actions are caused by our own desires, beliefs, and intentions, rather than by external coercion. In this view, freedom is about acting in accordance with one's own will, regardless of whether that will itself is ultimately determined. Another perspective, often associated with the A-theory of time, emphasizes the open and dynamic nature of the future. If only the present is real and the future is genuinely unwritten, then our choices can indeed shape what is to come. This view preserves our sense of agency and moral responsibility, as our decisions are seen as actively contributing to the unfolding of reality. The debate between free will and determinism is not easily resolved, and it continues to be a central topic in philosophy. It forces us to confront the limits of our understanding of causality, the nature of consciousness, and the very structure of the universe. The calm cosmos, in its silent, unchanging depths, invites us to ponder these profound questions, reminding us that the mysteries of time are deeply intertwined with the mysteries of our own existence. Perhaps the resolution lies in a more nuanced understanding of time itself. If time is an emergent property, as some quantum gravity theories suggest, then the deterministic nature of classical physics might break down at the most fundamental level, allowing for genuine randomness and the possibility of true free will. Or perhaps our experience of free will is a fundamental aspect of our consciousness, a subjective reality that exists within a larger, objectively determined universe. Regardless of the ultimate answer, the contemplation of time, free will, and determinism enriches our understanding of the human condition. It reminds us that we are not merely passive observers of the universe, but active participants in its unfolding, our choices, however small, contributing to the grand tapestry of existence. The calm cosmos, with its silent, profound questions, continues to inspire us to seek deeper truths about ourselves and the universe we inhabit. Our understanding of time is not solely shaped by scientific theories or philosophical debates. It is also deeply influenced by cultural contexts and historical developments. Across civilizations and epochs, humanity has conceived of time in diverse ways, reflecting different worldviews, societal structures, and relationships with the natural world. In many ancient civilizations, time was often perceived as cyclical, mirroring the recurring patterns observed in nature, the rising and setting of the sun, the phases of the moon, the changing seasons, and the cycles of birth, death, and rebirth. This cyclical view of time is evident in the calendars and mythologies of cultures like the Mayans, the ancient Egyptians, and various Eastern philosophies, where time is seen as an endless loop of creation and destruction, renewal and decay. This perspective often fostered a sense of harmony with nature and a focus on the present moment, as the future was seen as a repetition of the past. With the rise of monotheistic religions and the development of linear historical narratives, particularly in the West, a more linear conception of time gained prominence. Time began to be seen as a progression from a definite beginning, creation, towards a definite end, apocalypse or judgment day. This linear view emphasized progress, purpose, and the uniqueness of historical events, laying the groundwork for modern scientific thought and the idea of an evolving universe. The invention of mechanical clocks in the Middle Ages further revolutionized our relationship with time. Before clocks, time was often measured by natural phenomena or the rhythms of daily life. clocks introduced a standardized, abstract, and quantifiable measure of time, detaching it from natural cycles and making it a commodity that could be managed, saved, or wasted. This shift contributed to the Industrial Revolution and the modern emphasis on efficiency, productivity, and punctuality. Different cultures also exhibit varying degrees of monochronism, doing one thing at a time, and polychronism, doing multiple things at once. Monochronic cultures, often found in Western societies, tend to view time as a linear resource that can be divided and scheduled. Punctuality and adherence to schedules are highly valued. Polychronic cultures, prevalent in many parts of the world, tend to view time as more fluid and flexible, prioritizing relationships and simultaneous activities over strict adherence to schedules. These cultural and historical variations highlight that our experience of time is not merely a universal given, but a complex interplay of objective reality, cognitive processes, and societal constructs. They remind us that the way we perceive and interact with time is deeply embedded in our cultural heritage and shapes our worldview in profound ways. The calm cosmos, in its silent, timeless expanse, invites us to reflect on the diverse ways in which humanity has grappled with the enigma of time. It reminds us that our understanding is not monolithic but a rich tapestry, woven from scientific inquiry, philosophical contemplation, and cultural interpretation. This multifaceted view deepens our appreciation for the complexity of time, urging us to look beyond a single definition and embrace the myriad ways in which it shapes our lives and our perception of reality. In our profound exploration of time, from its cosmic origins to its subjective experience, we encounter a fascinating paradox. While everything within the universe seems to be subject to the relentless march of time, the fundamental laws that govern the universe appear to be timeless. The equations of physics, the principles of mathematics, and the very constants of nature do not age. They are, in a sense, eternal. Consider the laws of gravity, electromagnetism, or quantum mechanics. These laws are believed to have been the same at the Big Bang as they are today, and as they will be in the distant future. They do not evolve or decay over time. This timelessness of the underlying principles suggests a deeper, unchanging reality beneath the ever-flowing river of events. It implies that while the universe itself is dynamic and temporal, the rules by which it operates are fixed and immutable. This distinction between the temporal universe and its timeless laws is a source of both wonder and philosophical contemplation. It suggests that perhaps time is not the fundamental property of existence itself, but rather a characteristic of the particular configuration of matter and energy that constitutes our universe. If the universe were to cease to exist, or if it were to transition into a different state, these fundamental laws would presumably still hold, waiting to govern whatever new realities might emerge. The human quest for understanding is in many ways a pursuit of these timeless truths. Scientists strive to uncover the universal laws that govern the cosmos, seeking principles that transcend specific moments in time and apply across all of existence. Philosophers ponder the eternal questions of being, knowledge, and value, searching for insights that are not bound by the fleeting nature of human experience. Our ability to conceive of timelessness, to imagine a reality beyond the confines of our temporal experience, is a testament to the unique capacity of the human mind. It allows us to step outside the immediate flow of events and contemplate the grand, unchanging principles that underpin the universe. This intellectual journey, while challenging, offers a profound sense of connection to something larger and more enduring than ourselves. In the quiet moments of contemplation, when we gaze upon the night sky or delve into the abstract beauty of mathematics, we touch upon this timeless dimension of reality. It is in these moments that the calm cosmos reveals its deepest secrets, not as fleeting events, but as eternal truths. The pursuit of these truths is an endless journey, a testament to our insatiable curiosity and our innate desire to understand the universe in its entirety, both its temporal unfolding and its timeless essence. And so, as we bring this exploration to a close, we are reminded that the question of what is time really is not a question with a simple answer, but an invitation to a lifelong journey of discovery. It is a journey that takes us from the smallest quantum fluctuations to the grandest cosmic scales, from the depths of our own consciousness to the timeless laws that govern all of existence. May your thoughts continue to drift gently as you ponder the calm cosmos and the endless, enigmatic dance between time and timelessness.